Some of the boldest ideas in science come not from wild imagination, but from following the math exactly where it leads, even into invisible territory. Take the idea of multiple universes. It may sound like a science fiction add-on, an extra layer painted over reality to make things more dramatic. But in truth, it's baked into the equations themselves. Modern cosmology, especially the theory of cosmic inflation, doesn't just explain the large-scale structure of the universe we observe. It also predicts regions of space we can never access. Regions that inflate differently, evolve differently, and may never intersect with ours. They're not added on. They're results. Natural consequences of the same theory that explains the patterns in the cosmic microwave background and the distribution of galaxies. But here's the tension. What do we do with predictions we can't test? Science is built on a foundation of observation. You propose a model. It makes a prediction. You gather data. You compare. You revise. But what if a theory is extremely successful in all the parts we can observe and also predicts things we cannot? Do we reject those parts, or do we accept them as provisional truths, ideas that may remain untestable but still logically consistent with what we know? This is the current frontier of theoretical physics. The multiverse isn't a theory on its own. It's a consequence, a shadow cast by models that already describe our universe beautifully. To ignore that shadow may be to limit our understanding. To embrace it may be to expand science beyond the limits of experimentation and into the realm of pure inference. It's not just cosmology that faces this challenge. String theory, for example, proposes extra dimensions and a landscape of possible physical constants. Different regions of this landscape may give rise to entirely different universes, with different particles, forces, even laws. We can't observe those dimensions. Not yet. Maybe not ever. But they emerge naturally from the equations we trust. So the question becomes philosophical. What is science? Is it only what we can test, or does it include what we can logically infer from well-tested models? Some physicists argue for caution. If you can't test it, it's not physics. Others argue for boldness. If the model works and its implications are clear, we shouldn't flinch, no matter how strange the conclusion. And perhaps both perspectives are valid. Science must remain grounded, but it must also be curious. It must embrace the strange, without losing its roots in reality. The multiverse may be forever out of reach, but our thinking doesn't have to be. We can build models, sharpen ideas, explore consequences, and look for indirect clues. We can stretch our minds, not just our instruments, and in doing so, we become explorers, not just of space, but of possibility. This doesn't mean all ideas are equal. Speculation must be tied to evidence, even if that evidence is indirect. But sometimes following the math with discipline leads us not just to new discoveries, but to new questions. Not just answers, but frontiers. And when the best tools of science point to realms we can't see, maybe that's not a failure. Maybe that's the next step. The universe is vast. Our methods are humble, but together they can reveal truths that reach far beyond what light can carry.